advancing in the path towards giving a good definition for line, surface, and volume based on the idea of thickness. And this has taken us to define some other things, because we were speaking that thickness was something that was measured somehow intuitively perpendicularly. Mathematically, by the way, we speak of normal direction instead of perpendicular direction in some occasions. And this analysis about perpendicularity brought the idea of tangency, okay, as a straight line that was touching in just one point, or that was no cutting a given line in a given point, or a plane that was just touching but not cutting a surface, okay? And in order to define what a tangent plane or what a tangent line was, we have introduced the concept of approximating curved lines by means of straight lines, okay? With some strategies, procedures, even I could call them algorithms, that allowed us to approximate the curve or the surface even as much as we wanted, okay? To get as close as we want to the final curve or surface. This idea of approximation by straight lines or even by flat surfaces, triangles, we made an approximation to the sphere, or to this orange with triangles. We said that we could make some kind of net here made out of 100 points initially and then connect them drawing some kind of triangles. Those triangles would constitute a polyhedron involving the orange, and that would be the first polyhedron approximating our spherical surface. Then we could use, instead of 10 equidistant points to do this net here, we could use 1,000, then 10,000, with the idea of always unite them to draw, let's say, triangles that would define a polyhedron involving the orange in this case. And this we could do with almost any surface, as I can think of right now. So this idea of approximating by straight lines is more or less the idea we intuitively have of zooming in. If we zoom in enough into a drawn line with our mouse, if we want to, okay, on the screens of our computer, or just pinching with our fingers, okay, we see that the line becomes more or less, tends to become straight. So this idea is, I think, quite good in order to have to make yourselves an idea of what I am speaking about by this approximation by straight lines, okay? This we do also experience on Earth, okay? On the Earth, as we are zooming in a lot when we look around us, because we are very small and the Earth is very big, we perceive things, we perceive the Earth's surface as being flat. And only when very long distances are involved, as when we are looking into the horizon on the beach, is when we realize that something is not fitting, let's say, or not matching well with our preconceived idea of the Earth being flat, because we see that the mast of ships is disappearing beyond the line of the horizon, okay? That's how we can define, in fact, the existence of our horizon. It's not a problem that we have not good sight, but because when we see the mast of a ship, at the end we see as if it was falling, okay? And that gives us an idea of, yes, there should be some kind of curvature on this direction, okay? Those step-by-step strategies or iterative processes, if you allow me, have allowed us to give a preliminary notion of what a limit of a succession is, okay? As the something to which we are getting closer and closer in each step of this approximative process. On each iteration, we say, instead of using the word step, it sounds more mathematical, if you allow me, okay? This is fantastic news. The existence of limits, the idea of limit, is something great. Because most curves behave good enough as to be approximated by straight lines, okay? And that's going to bring about the idea of sampling, but in just a moment, okay? The idea of approximating by straight lines this curved line that is going up and down with its peaks and its valleys. It's quite intuitive, no? First we will be drawing lines to the peaks, okay, check, 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 and then we will be introducing some kind of approximation in the midpoint, okay, beep, beep, yeah, I think you know what I mean. And this we will be repeating once and once again till we get closer and closer to the line, and most of the lines allow this kind of approximations, okay? For instance, let's give a proper example here, which would be the sun elevation all through the year, okay? We can work out the elevation, how the elevation is, as we spoke about it when we saw spherical coordinates, okay? Something like how much do I have to turn upwards my vision, my view, in order to reach a point, okay? So this point has 0 degrees now, 10 now, maybe 45 degrees of elevation with respect to this line. It's the angle I have turned my head to look straight into it, okay? So the elevation of the sun changes with time and changes with the time of year, no? Changes with the hour, we'd say. So the 1st of Jan, we could find out mathematically a formula, let's say, that which will have as input the time and day of the year, okay, and would tell us which is the elevation of the sun at that particular moment. Mm-hmm. But we don't need, as we know that curve is, as I said, nice. It's a nice curve. We won't enter into defining what nice means, but you understand my meaning, no? Something which is nice, more or less steady, making changes, but more or less steadily, something like that. But instead of working out the formula, we could just sample, okay? We could measure which the elevation of the sun is, I don't know, at each hour of the year, okay? And we would have a graph in a chart, which is made out of straight lines connecting 13 hours 1st of Jan with 14 hours 1st of Jan on one direction, and connecting it with midday 1st of Jan in the other direction. And like that, we will connect all the points and draw our graph, let's say, okay? If we need more precision, we don't need to work out the formula. We just need to sample more, and we will get to know the position at the 1st of January at 13 hours, 30 minutes and 35 seconds, saying that it's going to be equal than the position at the 1st of Jan, 13 hours, 30 minutes and 0 seconds, because we know that the change made during that minute in the elevation of the sun is, how do you say it, despicable? I don't think you say despicable, but you know what I mean. It doesn't matter too much. Mm-hmm. So that's the idea of approximating by straight lines. Now that I think about it, maybe you would have understood it better with just my hands and my ball pen, okay? If we have this line, okay, we can define it, let's say, by the continuous movement of my hand, my fingers. But if I do like this with my ball pen, okay, you know also which line I'm describing, okay? The one that is, in fact, tangent is what you are imagining, okay? This line moving, the ball pen, it's involving the line, okay? And at some times when we speak of directions in curves or in surfaces, for instance, this curve, okay, we say, what's the direction here? Okay, the direction here in the surroundings of this point, okay, is that of this line, okay, is that of this line. And on times we say the direction in the limit, okay, in the surroundings of the point, in the limit the direction is. This will allow me to define what's the direction on this curved line, okay, here. The direction on this curved line in this point is going to be, in fact, a straight line, this direction, okay? And if I don't take the infinite number of directions defining this movement, but I just take some of them, some samples, pa, 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 the connection of these lines would be an approximation to the given curved line. Okay, but this I am insisting a lot because I am going to give you a counterexample, what in mathematics we call a counterexample. Okay, this idea applies in most occasions, but there are occasions where it doesn't apply. Not all lines are like that, even if you don't believe it, because at first sight everything seems to be approximatable. Everything looks as if it could be approximated by means of this trick of straight lines, and even not only approximated, but even with the idea of, yes, at each step we take, if I, instead of taking just this line, and this line, if I take more, tick, 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 I will be getting closer to the final curve. But this doesn't happen always. The case is the case of fractals, which deserve to at least to be mentioned. I am sorry to be extending, but this is the reckless maths, you know the drill. This, for instance, is a fractal. Okay, you are saying that we are drawing a triangle, and then we are drawing 3 interior triangles, and in each of these interior triangles we are drawing another 3 interior triangles, and so on and so forth and so on and so forth. If we zoom in, okay, if we zoom in this area, what will be seen? What will we be seeing? Almost the very same. And if I zoom again, the same. So this idea of zooming in that was very associated to the idea of limit and approximations here is not working. We are not getting closer and closer to an ideal straight line or nothing, because this, even if you don't believe it, is somehow a line. It's not a surface. Okay, we are not considering the interior. This area here, I'm going to use my red pointer. This area here doesn't belong to the curve, okay, or doesn't belong to the fractal, to be more precise. And it's obvious that it's not a volume, so it should be a line. We will speak about that later. But the idea is that fractals are not affected by zooms, and therefore the approximations we make to the fractal shape by means of straight lines are not so good as they were before in the case of our curved lines, okay? Even to make this even more complicated, this is made out of straight lines, but we cannot find a succession of straight lines. A little bit too much, but zoom is not working. That's what I want to highlight, okay? Zoom is just giving me the same and the same and the same. That what we just saw is the called Sierpinski triangle, okay? Other examples, not so geometrical as this succession of drawing 2 triangles inside, or 3 triangles inside a triangle, and then inside of each triangle drawing again 3 triangles, etc., etc. It's too geometrical. Let's try to find something more in nature, okay? The case of the coastline, I think, is a good example of fractals as well, okay? The shape of the coastline, of course, can be approximated, and we do that by means of straight lines. We just have to show the map, okay, to see a map. But that is true. But the idea here is that the most we zoom into an area, and I am not meaning on a map, I mean on reality, okay, the closer we get to that coastline, the very same amount of detail we are perceiving, okay? So normally when we zoom into a regular curve, we see less detail, we get closer to that straight line, okay? But here, as we zoom, then we realize that not up, it enters here, it enters there. It doesn't matter how much you zoom in. You can look to the coastline of the beach like this, and forgetting about a moment about the tide, okay, we will see that, yes, this area, it's humid right now, let's say, and this area should be the this line should be defining the coastline. But if I get closer, then I see that no, water got a little bit more inside here, and and we don't improve the level of detail remains with the same complexity, let's say, as we zoom in. This, I think, was also clearly seen when we spoke about the Sierpinski triangle. Okay, they are so weird that in fact we don't speak of them as being one-dimensional, two-dimensional, or three-dimensional shapes, but as if they were 1.5 dimensional, 2.5 dimensional, etc. I won't explain why, but you already saw on the Sierpinski triangle that something was weird there. And yes, it was made out of lines, but there were infinite lines. Poof. A little bit too much as to be calling it a one-dimensional shape. Therefore, 1.5 dimensions. The Sierpinski triangle has 1.5 dimensions. And the final idea of fractals I want to highlight is they don't get closer to a straight line as we zoom in with our regular, nice, smooth curves. The more there is a level, the more we zoom, the closer to a straight line we get. The more we zoom into a fractal, we don't get closer to a single straight line. And that's the idea. But getting back to our thickness thing, okay? We saw that, yes, we said at the beginning that, yes, that thickness should be measured perpendicularly. And we spoke of the normal, okay? And we said, yes, everything makes sense. And we brought the idea of tangency to a surface or to a line, okay, in order to help us to define which was the normal or perpendicular direction in which to measure thickness. But we said as well that somehow intuitively we spoke of measuring thickness in the direction towards the center. What center are we speaking about? In this is clear, okay, but in other shapes, as our wavy surface, is not so simple, or in a wavy line, same problem, okay? What's the center of this line? Once again, we are facing a property which belongs not to the line itself, but to points of the line, okay? For knowing which of what center are we speaking about, I just want you to imagine yourselves driving your car. I know you don't drive, or most of you shouldn't be driving, but you get the idea, okay? You are driving through this line, okay? If at a moment, as you are driving, your wheel gets blocked, you will start to describe a circle. You will get out of the wavy line and you will start to describe a circle. The center of that circle is the center we are speaking about when speaking of measuring towards the center. Okay, that's the idea. And the radius of that circle is what we call the radius of curvature. And 1 divided by that radius is the curvature. Okay, as simple as that. And I'm going to find a cable to speak a little bit more about curvature. I haven't found my black cable. Let's hope you can see this white cable here. As I said, curvature is the inverse, 1 divided by the radius of curvature, okay? And it's a property of the points, the curvature of this point. Right now, I don't know if you see it, it's in black on the cable, it's 0. And as we bend it, the curvature increases, okay? And if I increased it till a point where this would be an angle, an actual angle, then the bending or the curvature would be infinite, okay? And that's what was needed to know about curvature, okay? We will use this concept later on to speak about developable surfaces, but right now I wanted to introduce it as I am in need of curvature too in order to define volumes, surfaces, and lines. With the help of thickness and curvature, we can give good definitions of volumes, surfaces, and lines. At the end, despite thickness, despite curvature, despite approximation of lines by straight lines and surfaces by means of small triangles, small surfaces. Despite having introduced the concept of tangency and even the concept of fractals, it seems that we are where we started, with the idea of a volume being something with thickness and surfaces and lines being something without thickness. But we have introduced enough tools as to define properly volumes, surfaces, and lines right now. Okay, as follows. In fact, not as follows, because we have three different manners with the ideas we have introduced. First one would be to consider curvature, okay, and see that if you have thickness, you are a volume. If you have no thickness and just the points on your geometrical shape have one curvature, you are in a line. And if you have no thickness and the points in your geometrical shape have several curvatures, because for every point of the surface we will be having several lines, and therefore each point has several curvatures, then you are in the presence of a surface. This definition I don't like too much, because at the end it's playing with the idea of having several lines, a surface made out of lines that we already spoke about. But there it is. There is another, which was the one I thought at the beginning of this video I would be using, but now I have realized there is a better one, okay? But let's present it anyhow, which is to define a surface, for instance, this white thing here, okay, this white cylinder, I am touching with my finger, to define that surface as the limit of a succession of volumes that have less and less and less thickness. I would be, let's say, peeling this Scotch tape, first step, first turn, second turn, third turn, blah, 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 and we will be having less and less and less thickness, and we will be pointing, let's say, to the surface as the limit of a succession of volumes with decreasing thickness, okay? A horrible way, as I said on the slide, but to which now you are more or less prepared. Okay. In any case, I think I have found one which is better. I started to think about it when I saw this idea of having several lines in one point, okay, of a surface. It goes as follows, okay? If you have a geometrical shape and 2 points on that geometrical shape, and there is only, let's say, one way to get from A, the first point, to B, the second point, if there is only one way, you are in the presence of a line, okay? Then, if you have no thickness and given 2 points of the shape, you can get from one point to the other by different paths. I would even risk to say by an infinite number of paths. You are facing a surface. And finally, if you have thickness, you are facing a volume, and 2 points will be as well connected by an infinite number of paths. So this is the final idea of defining surface, lines, and volumes with the help of thickness. But let's deepen a little bit in it, because we can give it, I think, a better, let's call it shape, if you allow me. This deepening is to simplify things, okay, and came to my mind when I was thinking on the idea of having an infinite number of directions here. So wherever I looked in these directions, I would be finding points. That's what I thought, okay? So now, with this idea in mind, we can define properly volume, okay? A volume is a set of points that are surrounded by other points in any direction, okay? In all directions. If I am in the inside of a volume, wherever I look, I am going to be seeing points of the volume. In a surface, the things change a little, but not that much. In a surface, I can look into an infinite number of directions and find points. That's true, but not in any direction. Okay, I can look for instance, in this direction or in this direction or in that direction. Only the directions defined by the curves that are passing by this point, okay? In the directions of the tangent plane. Remember what we said, that the direction of a point of a line was the direction of its tangent, okay? And finally, what happens with the lines, with our poor old friends, the lines? In a curved line, if I'm in a point of a line, I will be looking at other points of the line. It is surrounded by points only in one direction. And that's the idea. That's the idea. I hope I had worked out this definition before, because it would have saved me the work of doing all this video. But on the other hand, we wouldn't have had the pleasure of knowing about cartography, of knowing about fractals, speaking about dimensions, etc., etc., etc. This is a little bit what I said about the pleasure of finding things out, okay? There I have had some pleasure on finding at least the definition I was looking for at the very beginning when I started with the idea of connecting points, etc. At the end, I think that for us, the students at KS4, the good definition of line, which is quite intuitive, is a set of points that are surrounded by points in only one direction. A surface, a set of points that is surrounded by points in an infinite number of directions, but not in any direction. And finally, a volume is a set of points, a geometrical shape if you want to, where points are surrounded by points in all directions. And that was it about surfaces. Last thing I want to do in this video, I will be doing it tomorrow, which is to speak a little bit about developable surfaces, and maybe a small, speaking a little bit more about cartography, okay? With that, we will be finishing the contents of this video, and then I will be speaking a bit about the pleasure of finding things out on space-time. But that's for another occasion.